Okay, so welcome to the afternoon session. The first speaker is François Gao from Nagoya University. Please start.
Okay, thank you. So I will talk about the classical algorithms for constant approximation of the ground state energy of local Hamiltonians. And so this is a work that has been published in the proceedings of this conference on algorithms. So I gave the talk last year in Poland, and it's also available on the archive. Okay, so I will start by giving a very rough statement of the first result. So we have two results. So I will first focus on the first result. So we consider a local Hamiltonian H acting on n qubits. And the locality will be constant, so really a very local Hamiltonian. And if you don't know what a Hamiltonian is, you can think of it as an Hermitian matrix of dimension 2 to the n, with very nice sparsity properties. And in particular, it can be described in poly n bits. So we have a computational problem where the input is described poly n bits, but represent a very huge matrix of exponential size. And we consider the smallest eigenvalue of the Hermitian matrix H, and we denote it lambda 0. So this is the ground energy of the Hamiltonian. And estimating this ground energy is really a central problem in quantum complexity theory and in computational chemistry. So it's a very important point, and a task that we really would like to solve on quantum computers or classical computers. And our first result shows that for any constant epsilon, there exists a classical algorithm, so it's really classical, that computes with high probability a good estimate of the eigenvalue, of the smallest eigenvalue. By good estimate, I mean an estimate lambda hat, such that the difference between lambda hat and the real lambda 0 is at most epsilon times the norm of the Hamiltonian. And epsilon here, again, can be any constant. And the time complexity of our algorithm is this. So 2 to the power big O of n, and the space complexity is polynomial in n. Okay, so this is the first result. And if we compare with the prior results, so priorly there were several classical algorithms. The first classical algorithm has complexity essentially 2 to the n time, so which is very good, but requires exponential space. So this is a classical algorithm based on Longsource method or the power method that will really work with vectors of exponential dimension. Another approach is to use a Feynman method. So this will give a very space-efficient method. And if you use the most efficient version of it, called the recursive Feynman method, developed by Aronson and Chen, you get polynomial space, but 2 to the big O of n log n time. Okay? So with our result, we get for the first time simultaneously polynomial space and 2 to a big O of n time. We combine the best of these two methods together. And there also exist the quantum algorithms for estimating this ground energy. So these quantum algorithms are based on the phase estimation. So usually you start with a random state, you apply phase estimation, and you obtain a random eigenvalue. And the probability to get the smallest eigenvalue is exponentially small. So you repeat this method an exponential number of times until you get an approximation of the smallest eigenvalue. So the complexity will be, the time complexity will be 2 to the power a big O of n, and the space complexity will be polynomial. So our algorithm matches the performance of this best quantum algorithm. But there is an important thing I would like to mention. So if you compare the precision, so in all those prior works, the precision is 1 over a polynomial, while in our algorithm, the complexity is constant. Okay, so we get very good time and space complexity, but the price to pay is to have a worse precision. Our precision is only constant. Okay, so this is the first result. So now I will state the second result. In the second result, we are considering a setting where we have an additional input. We know a vector, additionally, called the guiding state, that has some overlap with the eigenspace corresponding to the smallest eigenvalue. And this is really the main setting considered when discussing applications to computational chemistry. Because in computational chemistry, there are several methods to compute fairly good estimation of the ground energy. So this method typically gives you an approximate vector, an approximate eigenvector, which can be considered as this guiding state. And our second main result shows that, again, for any constant epsilon, there exists a classical algorithm that computes with high probability, again, an epsilon relative approximation, but this time the time complexity is polynomial in the inverse of the overlap, and n. And the space complexity is again polynomial. So by taking an overlap of 1 over 2 to the n, which is what happens when you take a random vector as a guiding state, you get the first result. So this means that the second result is a special case. The first result is a special case of the second result, okay? Obtained by taking as guiding state a random vector. And for this situation, previously, there was a classical algorithm obtained fairly recently by dequantizing the quantum singular value transformation. So that algorithm had polynomial space complexity, like ours, but has time complexity much worse. Okay, so we obtain polynomial in the inverse of the overlap in n, and prior work had this term in the exponent of n. So you get an improvement over the prior best classical algorithms, the first point. And the second point, if you use the same algorithm as the previous slide, the same quantum algorithm, but using the guiding state, what you get is a quantum algorithm with this time complexity and this space complexity. And you see again that our classical algorithm matches the performance of this best quantum algorithm. And again, the same thing, in our case, we achieve only constant precision, while in the quantum setting, the precision is better, okay? Okay, so this was the rough description of the results. So now, before explaining how we prove these results, I will give a few details about the setting and notations. So we consider an Hamiltonian, local Hamiltonian. We will write it as usual in this way. So it will the sum of m terms, where m is a polynomial of n, the number of qubits, and each hi is it's usually a matrix acting non-trivially on a few number of qubits, which means that it is a matrix containing at most a constant number of non-zero entries in each row and columns. So each hi is a very huge matrix, but extremely sparse. And we will normalize the Hamiltonian so that its norm is at most 1, so that we can say that all the eigenvalues are between -1 and 1. This will be easier for the discussion, but we can do it without loss of generality. And we are discussing classical algorithms. And in some cases, we will consider classical algorithm using a guiding state. So the guiding state is a very huge state of dimension 2 to the n. But when we consider classical algorithm using the guiding states, we assume that we have some special access to it called sample and query access. So if you don't know what it is, it's not important, but it's exactly the same kind of access as all the prior works on dequantization. So it's a really standard assumption in this kind of works. And so given a vector u of dimension 2 to the n, so we will write its conjugate transpose like this with a dagger, which means that given two vectors, u and v, the quantity u dagger v will represent their inner product. Okay, so I will not use a and the ket notations in this talk because we are considering classical algorithm, not quantum algorithm. So I will represent the vector by letter like this, and their complex conjugate transpose by this notation. Okay, so is there any questions at this point about the setting? Is it okay? Okay, so then I will try to give an overview of the proof. So roughly speaking, we prove our result by showing a reduction from estimating the smallest eigenvalue to iterated matrix multiplication. And this reductions goes through a series of simpler reductions. And the main technical contribution, the most difficult part is this one, so the third one. So, but I will start by explaining the two first reduction, and then I will spend some time explaining this most or main technical contributions. So I will start with really the first reduction here. This is actually a standard technique that has been used in several recent works on the quantum singular value transformation. I will try to explain it in one slide. So remember, the goal is to give an estimate of the smallest eigenvalue of the Hamiltonian. So rather than explaining how to do this, I will explain how to distinguish between these two cases. The smallest eigenvalue smaller than A, or the smallest eigenvalue larger than B, for some A and B, arbitrary, but with constant gap. And of course, if we can do this, if we can distinguish between these two cases for any AB, it's easy then to design an algorithm that will give an estimation, a constant estimation of the eigenvalue by using some kind of binary search. Okay, so the real task is really to distinguish between these two cases. Okay, so now H is a Hermitian matrix, so it has a spectral decomposition. I will write it in this way, the spectral decomposition. Of course, we don't know the spectral decomposition, but we know that the decomposition exists. And so the eigenvalues, I write them in this way, lambda 0 up to lambda 2 n minus 1, so in increasing order. And again, remember that we assume that the Hamiltonian is normalized, so all the eigenvalues are between -1 and 1. And now the crucial idea is to take a low-degree polynomial, P, satisfying three conditions. So first, in the interval -1, -1, 1, the polynomial should take value between 0 and 1. Okay? And then, second condition is that in the interval -1a, the value of the polynomial should be very close to 1. But in the interval b1, the value of the polynomial should be very close to 0. Okay? So this means that here it should be very close to 1, here it should be very close to 0, and in the middle between a and b, it can be anything except that it has to be between 0 and 1. Okay? So you see that this polynomial is actually acting as an approximation of the step function. Okay? Great. And we can show that it's possible to design such a polynomial by adjusting the degree. Okay? If you take a very high degree, it will be very, very close to a step function. If you take a lower degree, there will be more approximation here. But at the end of the story, we will adjust the degree depending on the input of the problem that we will consider. I will come back to this, how we set the degree at the very end of the talk. So now, the point is that if in the case where the smallest eigenvalue is larger than B, This means that you have lambda 0 here, and of course lambda 1 greater, and so on. Then we know that pH will be in, if you take the spectral decomposition, it will be a diagonal matrix where the diagonal entries are the polynomial p evaluated at all these eigenvalues. But since all the eigenvalues are greater than b, and we have the second property for p, this will be essentially 0. Okay, so if lambda 0 is larger than b, then pH is essentially the 0 matrix. On the other hand, if lambda 0 is smaller than a, so you see lambda 0 here smaller than a, then if you look at pH, you will have at least one diagonal matrix which is very close to 1. Okay. So this is a crucial property that we need. And more generally, for any vector u, an arbitrary vector u, if you look at this quantity, so this quantity u dagger pH u, this means you have a vector here u, you apply the matrix pH, and then you apply u dagger, so you obtain a number, right, a scalar. So if you look at this scalar, so for any vector u, it will be very close to 0 if lambda 0 is larger than b. And if lambda 0 is smaller than a, then it will be at least the overlap between u and the eigenspace corresponding to lambda 0 for this, from this second property. Okay, so we have now a nice criterion to decide whether lambda 0 is large or small. And we see that what we need to do is to compute this quantity. Okay, so the inner product between u and phu, these two vectors. Okay, and of course, we need to explain what vector we will choose. And I will come back later, but I can tell you at this point that for our first result, we will use u, choose u as a random vector. But for our second result, we will use u as a guiding state provided as part of the input. Okay? Okay, so now I will go one step further. So remember, p is a polynomial. Okay, so px can be written like this with some coefficient a0, a1, and ad. So this means that this inner product can be decomposed as a sum of d plus 1, where d is a degree here, d plus 1 inner products. And what we will do, we'll compute each of these inner products. So we'll compute this quantity here for each r from 0 to d separately. And once you have a good estimate of all this d plus 1 inner product, we will compute this quantity by using this sum. Okay, so this reduces the problem to the task of computing this inner product. Okay, so I am at this point. At this point, I have explained how to reduce the estimation of this eigenvalue, the smallest eigenvalue, to the computation of this quantity for each r from 0 to d. And now I will explain how to do it.
すみません。SIM カードがありますか? Or do you have SIM card in this shop? SIM card. SIM card. No. Thank you.
Yeah, so there is somebody with a mic on. Maybe you can put the mic off.
Excuse me, Hayashi sensei?
I think it's Yutao Lee, maybe?
Yeah. Only Hayashi sensei can
Okay.
meet. So,
Okay, thank you very much.
yeah, thank you.
Thank you. Okay, so now I will explain the main technical contribution, which is this part, how to reduce this task to this task. Okay. So we want to compute this quantity. And remember, H, we know it's an Hamiltonian, so it's a sum of a polynomial number of extremely sparse matrices Hi. Okay? So we will use this property. And we can rewrite this, this quantity, what we want to compute, in this way. And then we can expand, and you will get a sum, actually R sum here, okay, of terms of this form. And now the key insight is to consider a probability distribution, to introduce a probability distribution from the set of indexes here appearing in the sum, which is defined as follows. So for x, so x is a set of one possible set of indices. For each x, I define qx as this. So it's essentially the norm of the matrix appearing here in the sum for this set of indices. And we can check that it is a probability distribution precisely because we are assuming that H, the crucial thing is that H, we are assuming that it is normalized Hamiltonian. So since it's normalized Hamiltonian, we obtain a probability distribution. The sum of all the probability is 1. Okay, so you have this. And now I consider the following random variable. So I consider this quantity here, this quantity dividing by qx. And here I'm taking x sample from q. Okay, so I first sample x from q, and then I output this quantity. Okay, what is the expectation of this random variable? So the expectation is very easy to compute. It's a sum over all the x of qx times the quantity. And you see that the qx disappear, so you have the sum over all the x of this. And you see that this is exactly what we want to compute because you have this equality here. And the variance, you can show that the variance is relatively small. So what you get is a random variable with expectation, which is exactly what we want to compute, the quantity we want to compute, and very small variance. So this means that taking the mean of a small number of samples will give you a good estimate. You can show this very easily by using Chebyshev inequality. Okay. So what you need to do is to sample x from q, which is actually easy because we know all those norms, and then compute this variable. So dividing by qx is easy, but we need to compute this term in the numerator. Okay, so the main computational difficulties is to compute this term. Okay, so now I have explained a reduction from this, what we wanted to do, to computing this quantity. Okay. So finally, so how to compute this quantity? We will use a theorem, recent theorem by Ewing Tang, saying that for any two vectors, you can compute a good estimate of their inner product very efficiently if you have sample and query access, what we call sample and query access to U, and query access to V. And by assumption, we have sample and query access to U, so it's okay. So you just need to implement query access to this vector. What does it mean? We need to be able, for any index I, to compute the ith entry of this vector. Okay? I don't ask to compute the whole vector because the whole vector has exponential dimension, so it would take exponential time, which is too much. I only ask you, given a specific I, to compute the ith entry. And this is iterated matrix multiplication. You know U, and you have to apply R matrices to the vector U. But the key property that we can use is that each matrix that appear here, each of these R matrices has at most a constant number of non-zero entries in each row and column. Okay? And then a very careful implementation of the standard algorithm for matrix multiplication will not work. But if you do a careful recursive implementation, this will give you an algorithm with time complexity which has complexity s to the power r, where s again is the sparsity of each matrix, which is constant, so constant to power r, and the space complexity will be very efficient. Okay, so we do get this complexity because of the property that each matrix appearing in the product is extremely sparse. It only has a constant number of non-zero entries in each row and column. Okay, so let's summarize what we have done so far. I have explained how to reduce the estimation of the ground energy, the smallest eigenvalue of H, to iterated matrix multiplication, actually D plus one instance of iterated matrix multiplication. So the complexity of this D plus one instance will be for the first one this, for the second one this, and so far. The time complexity and polynomial space. So the total complexity, if you look at the sum here, it will be s to the d, s to the power d, time d, time, and polynomial space. Okay? Because all the other steps are fairly straightforward. Really, the most time-consuming and space-consuming step is the final iterated matrix multiplication that has this complexity. Okay, so you see that the complexity depends on d, and d is the degree of the polynomial p. Okay? And again, p is a polynomial that is expected to approximate the step function. If d is very large, then you obtain a very good estimation of the step function, but the cost here will be very high. If d is smaller, you get a very good complexity here, but the approximation of the step function can become worse. So we have to find the optimal value of d that gives enough accuracy and as low as possible time complexity. And this depends on the setting we have. So for the second result, when we have a guiding state, we will take for u the guiding state u, and you can show that you can take d of this order, okay, where chi is the overlap between the guiding state u and the eigenvalue corresponding to the ground state energy. So if you take d of this order, then you will have a good enough estimation of the step function, and this will lead to a total complexity of, so if in the case where s and epsilon are constant, what you get is constant times this, so constant times the log of 1 over chi, which gives you polynomial in the inverse of chi and n. Okay, and polynomial space, of course. So now, for the first result, where we don't have any guiding state, we will take a random vector. And you can show that with high probability, a random vector will have an overlap of order 1 over 2 to the n with the eigenspace corresponding to the ground energy. So by replacing this chi here by 1 over 2 to the n, you get d equal a big O of n over epsilon. And again, when epsilon is constant and s is a constant, when you plug in this expression, you get complexity 2 to the big O of n time. And again, polynomial space. Okay? So to conclude my talk, so we constructed classical algorithms approximating the ground energy of a local Hamiltonian for two settings. The first setting without guiding state. In this case, the time complexity will be exponential, but we will have polynomial space complexity. And the second setting is when there is a guiding state. Then the time complexity will depend on the overlap parameter chi between the guiding state and the eigenspace corresponding to the ground energy. But the point is that in both settings, for constant precision, our algorithms improve previous classical algorithms and match the performance of quantum algorithms. Okay? And our main insight is to use sampling, exploiting the fact that a local Hamiltonian is a sum of extremely sparse matrices. Okay? So by using sampling, we don't have to compute anything. Essentially, by choosing cleverly the probability distribution with the sampling concentrating the weight on the matrices in the sum that have the highest weight in some sense. And that's how we can obtain a speed up with respect to prior algorithms and match the performance of quantum algorithm, again, only for constant precision. And the main open question I have is understanding if our algorithms are practical, okay? Because all algorithms improve classical methods for constant precision. So a priori, they should be, they are the best known and the fastest known techniques to compute approximation of the ground energy of Hamiltonians, if you want only a rough precision. So it will be really nice to implement this on real problems and to see how do they compare in practice to the best known approaches. In theory, they are the best, but what's happened in practice? I think it's a very important open question. Okay, thank you for your attention.
Thank you. Is there any question? Can I ask one question?
Sure.
So in the case of local Hamiltonian, especially geometrically local Hamiltonian, so
Yes.
one could expect like lowest energy subspace kind of spanned by low entangled states. So maybe could you improve the sampling of totally random vector to random but only low low entanglement states?
Yes, it's a good point. Yes, we haven't really. Yes, it's a very good thing. Let me go back here. Yes, probably here. So our second results say, assume that we know a vector that has some overlap, then the complexity we get in this thing. Okay. We do not discuss how to compute or guess or obtain this guiding state. But as you mentioned, in practical scenario, we often have a very good overlap if we take a simple families of states. So it will be really nice to identify all those cases for which we can get a very good guiding state from the start and obtain an explicit complexity, not depending on the parameter chi, but really depending only on the parameters of the Hamiltonians. And this might be possible indeed for some special classes of geometric Hamiltonians.
Okay. Or maybe, in practically the true, ground energy is not so important, only, the lowest energy in terms of restricted Hamiltonian, restricted on low energy, low entangled subspace would be enough, I guess.
Okay, yeah, yes, it's a very good point. Yes, we haven't really explicitly considered this in this work, but I think the algorithm should work. If you restrict, if you really find, if you can generate, say, a random low entanglement state in some good ways, then this will give a speed up with respect to what we obtain. Yes.
Thank you.
Yes.
Is there any? Yeah, sorry.
No, thank you for the suggestion. Yes, it's a really nice suggestion.
Is there any question from Zoom?
Sorry, I have a question. So this algorithm, okay, so this algorithm calculate the minimum eigenvalue. So also, can you calculate the how to say corresponding to the eigenvector. How about the calculation of the eigenvector?
Yes. So first, the eigenvectors are very high dimension, right?
Huh?
The
Oh.
dimension of the eigenvector is very large.
Oh.
It's exponential
Yeah.
dimension, so it's difficult to, I mean, in polynomial time, you cannot really do this. But something that can be done is to try to simulate, to implement a projection into the subspace corresponding to these eigenvectors. And I think this is also possible with the same technique. So not really find the eigenvector because they are too high dimensional but implementing an approximate projection into the eigenspace of the eigenvector should be doable.
I see. Okay, I understand. But I think in the quantum case, that algorithm can output that eigenvector, I think. But
Yes.
identifying that eigenvector is extremely difficult in the quantum case.
Yeah, exactly. Yes.
So
You
this is
get,
a very serious disadvantage in the quantum case.
yes. As you said,
But but in this classical case, you can identify a partial information of the eigenvector. So this one is much strong advantage, I think.
yes. I'm not sure it's give really. I would say you obtain the same kind of performance in both the classical and the quantum case. But for example, what we are doing in this work is approximating the eigenvalue, and quantum algorithms also do the same. They give a classical value, classical output. So we are doing the same. If we want to find the eigenvector, classically we need exponential time because it's a very, very big thing that we need to output. Quantumly, it will be the same. If you, as you said, you can create a quantum state which represents the eigenvector, but if you want to extract information, you need to measure it an exponential number of times and so on. So I think what we are doing here is more or less matching, doing exactly the same as a obtaining the same performance as a quantum algorithm.
I don't think so. I don't think so. Even though quantum case, you could output the quantum state, but it is not so easy to identifying the partial information.
Yes.
But in the classical case, I think not so difficult.
Yes, maybe yes. Maybe
Because
possible.
identifying the quantum state is sometimes quite difficult. So
Yeah, sure. Yes, there may be indeed some setting where you do get some advantage. It would be very nice to really identify precisely what we get. Because it will give the case where you have a quantum advantage in some sense. Maybe not against all quantum algorithms, but at least against known quantum algorithm based on the phase estimation.
I think so.
Yes.
Any other question? If not, let's thank the speaker again.
Thank you.
So the next talk will start in like 10 minutes.
Hello.
Okay, the time has come, so let's start the next talk. So the next speaker is the Taka from Nagoya University. Please start.
Thank you. Yeah, so the title of my talk is Group Order is in QCMA. This is a joint work with François Lugal and Harumichi Nishimura. Yeah, so let me start with a basic definition of groups. A group is a finite set with a binary operation, and this finite set should satisfy certain properties. One is closure, associativity, identity, and inverse. And such a set with satisfying these properties, we call it as a group. When we talk about algorithms on groups, we have to specify how we will give our group as an input on algorithm. So this is called group representation. There are multiple ways of representing a group to an algorithm. One of them is Cayley table representation, where we have given a whole table, multiplication table of the group explicitly. Then there is permutation group representation, where we have given a group G by a generating set, and each generators are permutations on n symbols. Then there is this matrix group representation, where instead of permutation, we have matrices as a generating set of G. So G is a subgroup of general linear group. And the most general representation to represent a finite group is a black box group representation. I'll define this representation in the next slide. But before that, let me mention that depending on what representation we are using, a computational problem might be very easy or extremely challenging. So it is better if we fix the representation at first. And as I said, this black box representation is one of the most general ways to represent finite groups. In this representation, again, we have given a group G by a generating set, but now each element of the group G is represented by a binary string of length order log mod G. And we have two oracle that will be available at unit cost. One is multiplication oracle, where given any two element G and G prime, this oracle will compute its multiplication. So it will give us a string of G prime. And the other oracle is inverse oracle, where given any element G, this will compute a string representing G inverse. And in the quantum setting, we can feed G and quantum superposition of G and G prime, and the oracle will compute the multiplication or inverse oracle, inverse of the element. And in the quantum setting, we also have to make one more assumption, that each element here is encoded by a unique binary string. And this is an assumption that is already there in all the prior work that has studied group theoretic problems from quantum perspective, quantum complexity perspective. So this is the model of computation. Our group is given by a black box representation. And since so we can show that this T is at most log mod G, so the input size will be order log mod G square, because each Gi can be represented by a log mod G length, and T is at most log mod G, so the input size is log mod G square. So the problem group order is defined as follows. As an input, we have given a group G, and it is given by a black box representation, and we want to compute its cardinality. And to solve group order problem, we can also study the decision version of the problem, where we have given a group G as a black box representation, and we have also given an integer m, and we want to decide whether size of the group is m or not. So this problem has been very well studied from complexity theoretic point of view. So for cyclic groups, there is an result which says that it requires exponential time to compute the order of the group, exponential in the input size, which is log mod G, poly log mod G. And the best upper bound is AM. So computing an order of a group is known to be in AM. And from quantum complexity theory, there are polynomial time algorithms which is known to compute order of a cyclic group, abelian groups, and also solvable groups. So from this figure, it is clear cyclic groups are more structured group, and then there is abelian group, and which also captures a solvable group. So abelian group are inside solvable groups, and then we have finite groups, all finite groups. So there was an open question that can we compute order of a group G for arbitrary group for any arbitrary group G, whether it is in QMA or not. And our result shows that computing an order of arbitrary group G is in QCMA. So I'll go into the proof idea behind this result, but before that I'll mention one consequence of this result to one of the most interesting problem in quantum complexity theory, which is known as group non-membership problem. So group membership problem is defined as follows. We have given a group G by a black box representation. We have also given a subgroup H of G and an element G in G, and we want to decide if G is in H or not. And in the group non-membership problem, we want to decide if G is not in H. So group membership problem is already known to be in NP, but group non-membership problem was known to be in QMA. And it is also known that by Aronson and Kuperberg, they show that in fact group non-membership problem is in QCMA under some group theoretic assumption. And then they conjecture in the same paper, they conjecture that this group non-membership problem is in QCMA. And our result solves this conjecture by using an algorithm for group order. We can actually solve group membership because of this observation that checking if an element is in H is equivalent to checking, computing an order of the group which is generated by H and G. So G is in H if and only if the order of H and the new group H together with G are same. So if we can compute the order, we can test group non-membership, and that gives group non-membership is in QCMA, which solves the conjecture. Now I will speak about, I'll briefly mention the proof idea behind of our result. So we want to solve group order verification problem where we want to decide whether our group is order of the group G is M or not. So it is enough to solve these two sub problems, which is first is group order divisor verification, where we want to decide whether M divides mod G or not, and the other is group order multiple verification, where we want to decide if G divides M or not. So the first problem, which is group order divisor verification, is relatively easy than the other task. Let me briefly mention. So what we can do, we want to decide whether mod G M divides mod G or not. So we first we can compute the factorization of M. Let us assume that M factorizes as follows: P1 A1 to PR AR. Now it follows from group theory that M divides mod G if and only if G has a subgroup HI of order Pi to the power AI for each I. And all the groups of order Pi to the power AI are solvable groups. This is a fact from a group theory. It is easy to see. And what we can do now is we can ask prover to send us generators for each subgroup HI. And now we have to verify whether each HI is a solvable group, and then we have to verify its order is Pi to the power AI. But for this verification procedure, we can use Water's algorithms for solvable groups, which is already there in the literature, which solves the group order divisor verification in QCMA. So the next task is to show group order multiple verification is in QCMA, and that is the remaining part of the talk. So before I describe the proof strategy of theorem 2, let me mention two definitions. A group with no non-trivial normal subgroup is called simple group, and a composition series of a group G is a list of subgroups H0 to Hs satisfying these two property that we have a series of subgroups starting from identity to G, and each HI is a subgroup of HI plus 1. And the factor group or the quotient group, HI quotient HI minus 1, is a simple group. Now, if we have a composition, it is not known to compute, like we cannot compute a composition series efficiently. But suppose we can compute composition series efficiently, then we can compute the order of the group G by computing the order of each of this factor group. And this definition of composition series suggests a strategy to compute mod G. And that is as follows. So we can ask prover to send us a composition series, that is a series of subgroups HI, these HIs, and we have to verify that each factor group HI quotient HI minus 1 is simple, and once we verify that, we have to compute its order. But the second step is not as easy as it sounds. So let me mention. So since this HI quotient HI minus 1 is simple group, we can use properties from group theory, so in group theory there is a theorem, a classification theorem of finite simple group, which says that all the finite simple groups, so it classifies all the finite simple group, and it says that any finite simple group can be one of the 44 families. Out of those 44, 26 families are called sporadic simple groups. Those are of constant size. And there are only 18 infinite families which are infinite, so it's not a constant size. And since this factor group HI quotient HI minus 1 is simple, it should be one of these 44 families. So then we can modify our strategy using this classification theorem. As follows. So we can ask prover to send us a composition series and also the standard name of the simple group, say WI. By standard name, so one of these 44 families, so which family it belongs to. And then we will check whether HI quotient HI minus 1 is isomorphic to a simple group with standard name WI or not. And to do this verification, suppose this HI quotient HI minus 1 is one of the constant size simple group, then this verification is easy because it has constant order. And so we have to handle the remaining 18 infinite families. Out of those 18 infinite families, for 17 infinite families, we can do the verification efficiently. It is not trivially, it doesn't follow trivially, but we can do it using some results from the literature. And it also uses a specific fact that all of these 17 infinite families admits a short presentation, and which we can use to verify whether our factor group is one of those 17 infinite families or not. But there is one more family of one of the 18 infinite family. There is one family of free groups for which we do not have this spatial presentation or short presentation, and we have to handle or we have to verify our factor HI quotient HI minus 1 is isomorphic to regroup or not efficiently. And to do that, that is one of the difficult part. And to do that, we designed a randomized homomorphism test, which I'll describe what is the randomized homomorphism test. But before that, so the family of free group is generated by these 3 spatial matrices, and it is you can see it as a subgroup of GL7Q. And we will not need the presentation, but it has a genetic set of size 3. That is all we need. Okay, so to handle this family of free group, we designed this randomized homomorphism test, which is as follows. So our goal was to check our group sigma, which is a factor group HI quotient HI minus 1 is isomorphic to a group S and S is regroup. So what we can do, we can ask prover to send us generators of sigma, G1 to Gk k many elements from sigma, and if sigma is isomorphic to S, which is regroup, then and prover is honest, then it has then prover has sent us a generators Gi such that there is an isomorphism from simple group to from regroup to a group sigma. And in the checking procedure, what we have to do is we can define a map F from S to sigma by extending the map Si goes to Gi. And to do that, we have to have this property that for any element S in S, we have to write S as a product of generators of S, generators Si S1 to Sk. And once we have this representation of S in terms of generators of S, we can define f of S to be equals to f of Si's. And then we also have to verify that our f is homomorphism. So for that, we can take arbitrary element S and S prime and check if it satisfies this condition of homomorphism, and checking whether this this equality holds is same as checking whether this element is in the spatial group Hi minus 1. So it reduces to membership in Hi minus 1. Now, I'll not go into the detail of how we will verify all these things, but what I will mention is that the difficult part in this verification procedure is to check this equality, which reduces to membership testing in Hi minus 1. And membership testing in Hi minus 1 is, in general, it is not easy. So we reduce the membership testing in Hi minus 1 to membership testing in a solvable group H0 using technique from Babai and Bills. And yes, so here what we have shown using Babai-Bills filtration, what we have shown is that the factor group Hi quotient Hi minus 1 is isomorphic to another factor group. So membership testing in Hi minus 1 is reduces to membership testing in H0, but now H0 is a solvable group. And we have a membership testing in solvable group from Water's paper, which is BQP, quantum polynomial time. So we can use a membership in H0, and we can use our randomized homomorphism test to handle the regroup case, which was the difficult part to have QCMA protocol. Yeah, so that is all. That is how we design, we obtain that group order multiple verification is in QCMA. So to conclude my talk, we studied two problems, which is group order verification and group non-membership problem. And we show that both of these problems are in QCMA. Thank you. Any questions?
Thank you. Any question? Can I ask a naive question? Maybe I missed in the talk, but how can you determine the sequence of the normal subgroups?
Yes, we are not determining. We are asking
Given?
prover
Oh,
to
okay.
give us the subgroup, but we have to verify. I have skipped a lot of details from the paper, so we have to verify this sequence is actually a sequence of groups which we need.
Have the decomposition or not?
Composition.
Okay.
Sorry, I have one question.
Yes.
So I could not get the essence. So you considering so many kind of the classification part. So this part is purely related to the mathematics. So once so there okay. So I want to understand much most simple situation. So there is no that kind of the hierarchy. So only the just one. So there is no subgroup. In that case, what you can do? So could you explain the most simple case? There is no trivial, there is no non-trivial subgroup case. In that case, maybe your protocol is quite quantum. So we don't need to employ the quantum, that classical discussion. mathematical discussion.
Sorry, I'm not getting your question. You are asking if G does not have any proper normal subgroup, so we do not have any.
Yes, no subgroup case. So in that case, the problem is much simpler. So please explain that special case.
In that case, we still have one factor which is from identity to G, right? So G itself will be a simple group, but that could be a regroup. That simple group could be a regroup. So we have to identify what is G.
So but I could not find your quantum protocol. So everything looks like quite mathematical. So there is no quantum algorithm. So could you explain the quantum algorithm? That case is most simple case. That M is a prime number. So prime number case. I want to understand the M is a prime number case.
If M is a prime number, then it is cyclic group. So simple group, but also it is cyclic group, and that is already known to be BQ.
So could you explain that protocol?
Which?
This is the existence protocol. Then you didn't explain your paper. So in your paper, in your discussion, you how to say record that existence method. So then other part is quite mathematical. So then you have no essentially quantum protocol.
So in our protocol,
quantum part is rely on the existence result.
Sorry, if I am getting your question correctly. So in our protocol, we use quantum polynomial time algorithm as a black box. That is the quantum part. Otherwise, it is classical. And if you're asking about the simple case, there can be two simple case. Either it is of order P, where it is cyclic group, and there we can solve it using Shor's algorithm. But G, if it is of order P, then it is cyclic group. But it can be a simple group which is not of order P. So it's non-abelian simple group. And there we have to use our protocol. That simple group could be any of these families.
If that hierarchy is quite simple, so in that case, it is enough to employ Schwar's algorithm. I see.
Or the solvable membership problem, right?
Yes. Even if all of these factors are cyclic, that means that group is solvable. Even then, the algorithm is known to be quantum polynomial time by Waterhouse.
Okay, so you can employ the previous.
Yes, but the problem is this factor group will not be always cyclic for arbitrary group. And that is why we have to use the protocol.
Is there any? Please have a.
Anyway, so I because there is no quantum discussion, so quite confused. So.
Yeah.
So you recall that quantum protocol as a sub protocol. So.
Yeah, in the verification procedure, we use quantum algorithm as a black box. That is the quantum part.
But you didn't explain that quantum part so explicitly.
Yeah, but for that I have to inform. I have to mention a lot of things. So and it was not possible. So I just mentioned the main part, which is this goal. And yeah, so as I mentioned, the main problem was one of the main problem is to check this homomorphism condition, and there we reduce checking arbitrary membership into checking membership in solvable group, and that is the quantum result we are using. Once we reduce membership in solvable
so which one is the quantum algorithm? So which sub protocol is quantum?
So one of the part in the verification procedure is to check whether this map we are defining is actually a homomorphism, and to do that we have to verify few conditions, and one of them is this condition, which is same as checking membership in hi minus 1, but we reduce this membership checking in hi minus membership in hi minus 1, we reduce this to checking membership in h0, which is a solvable group, and now we are using already known quantum algorithm, which will check membership in H0. And that is quantum algorithm by what?
I cannot understand which one is quantum algorithm. Please explain more simply. So you answer so many things.
Okay, so let me try. Sorry. Yes, so in the verification procedure, there are a lot of things that we have to verify.
Please answer only one thing.
Yes.
What simple quantum algorithm you employed?
Membership in solvable group and computing order of a solvable group. Those are known to be quantum polynomial time, BQP, and that is we have used as a black box.
So this one is known result. Who proved this one? Who showed this?
Waters 2000.
So please show me that one. That's the result.
Result by Waters?
So please show me that existent result you employed.
Yeah, it is this paper from by Waters, succinct quantum proof for properties of finite groups.
So
Okay, so the time has come, so let's thank the speaker again.
Thank you.
Next talk will starting from 50.
I just request to share my screen.
Yes,
Do you
yes.
have to agree? Okay, I have to.
Do you have a authorization? Can you share the screen now?
Okay. Host, it's allow
this
me to
platform?
share. Okay, just the multiple sharing. So do you enable to that enable to me to share the screen? It shows that it's a multiple sharing.
Oh. Okay, we are stopping sharing.
Okay, it's good now.
Yeah, we can see. Okay, we will start in 2 minutes.
Okay.
Okay, so the next speaker is Jun Ki from Hong Kong Baptist University. Please start.
Okay, thank you. Good afternoon, everyone. So my topic today is about quantum machine learning, especially just using some tensor networks to set up a hybrid architecture to implement a scalable and a robust, resilient quantum computing architecture. So my research is a little bit different from the others. The other thing is mathematics. My research about is engineering oriented, but I will share some proof to verify why my architecture can work so well in theory, but I'll also give you some empirical results to demonstrate its quantum advantage. So let's say my research can be consist of two parts. I briefly introduce the quantum enhanced machine learning, and my research focus about is machine learning for quantum. I just place my research in a big picture. Nowadays, my end is a generative AI. It's about from 2010, we just witness a rapid development of deep learning. Every 35 months, every 80 months, we see that the model size can increase by more than 35 times. On the other hand, we see that the computational computing power can now catch up with the development of deep learning development. Because it's a classical computing that based on Moore's law, every 80 months, the computational power can be double. So the gap between the requirement for the large language model and the development of this classical computing power is becoming larger and larger. So that's why we tend to choose some quantum computing. Maybe we can do some research about neuromorphic computing and conventional computing. But quantum computing is very promising. In factor time, is found this Google's the video. 2 years ago, it's actually enabled the logic qubit. It's by using some many hundreds of thousands of physical qubits, which are synthesized, so one or two is a good logic qubit. So by scaling up these physical qubits, it can enable this quite rapid development of logic qubits. Nowadays, we just in the year of 2025, we witness an exponential increase of quantum computing. Somehow, the quantum computing can take over the classical computing to put forward development of machine learning, optimization, or do simulation. So that's why I do about this quantum machine learning. It's especially based on this how to do the intersection between quantum computing and machine learning. Okay, the first this research paradigm is a quantum enhanced machine learning. In such a this research paradigm, we just set up is a hybrid, the quantum classical architecture. So some components is composed of the classical components by using some classical neural network, by using some tensor network. It's based on the CPU and the GPUs. But the more important thing is that we just build up some quantum components to just set up the hybrid model. Some components just belong to this classical one, and some components belong to this the quantum component. So they're using some classical component, we can do some dimensionality reduction and the feature extraction, or maybe just introduce some nonlinearity before these quantum components. But we use a quantum classifier to enhance the machine learning performance. So we have one paper is showing such an unconventional hybrid quantum classical architecture for scalable and robust quantum machine learning using such architecture. Another thing, we just do the opposite. Instead of just using the quantum computing to enhance machine learning, we want to do the opposite thing. We want to leverage the classical machine learning to put forward development of quantum computing. So everyone should be very familiar with the classical machine learning theory, and machine learning algorithms. Although we just see that the theoretical study of classical machine learning is far behind the empirical study, the gap is still very large, but we can just transfer some theoretical study to put forward development of quantum neural network, quantum kernel methods, and quantum machine learning architectures. So we just using some of the theoretical study from this classical neural network to put forward development of quantum neural network, how to just scale up both theoretical study and empirical study. So this my research focus. I have 2 papers, 2 MPG quantum information papers about this. And also this focus of this research, of this talk, how to just use some classical neural network and the classical tensor network to scale up the quantum neural network. How to just use the classical algorithms to just set up unconventional architecture to just let quantum neural network to be noise resilient. So nowadays we just on the ISCO era, it's a quantum noise is an important issue. So but we can just set up unconventional architecture to be resilient to quantum noise. Okay, as a get started to this first research paradigm, just very go quickly to the first one, and maybe just give you some more time to this second one. About 6 years ago, we had the first group of people to use about 10 qubits on the IBM quantum experience. It's an IBM cloud to set up the first generation of the quantum machine learning. At that time, we just use 10 qubits to physical qubits to just implement the real is a quantum reinforcement learning. At that time, we just simply do the replacement. We just replace the classical neural network with such as a quantum circuits. So quantum circuit here, we just use some the quantum circuits to do this the data conversion from this classical data to this quantum data. We use some this rotation gates to just set up this trainable gates, and in between we have some this entanglement gates. We use 2 qubit gates to implement this entanglement gates. So just use such as a variation quantum circuits to replace the classical neural network to implement such as a quantum reinforcement learning. And I was about 6 years ago, we just used 10 physical qubits. And our performance shows that even though we do such a simple replacement, our the reinforcement learning system, the performance can be maintained. It's about 6 years ago, by the first group of people to implement such a thing. About 5 years ago, we also do similar thing, but here we just set up is a quantum convolutional neural network. Here we just simply just replace the classical kernels with quantum convolutional kernels. So we use quantum circuits to just set up these quantum kernels. So this instead of using the classical kernels, we just use quantum kernels. So the features are quantum encoded features, quantum enhanced speech or image features. Use such a quantum encoded in classical image speech features go through the classical classifier, which shows that the quantum encoded features can be more discriminative and more representative. So this about 5 years ago, we just set up this quantum convolutional neural network for this to enhance the machine learning performance. Okay, last year, we just consider to set up this unconventional hybrid quantum classical architecture. So everyone should be very interested about this ChatGPT or large language model. But bottom line here is that we have to face billions, 10 billions model parameters during training. So the challenge here, how to just use these quantum circuits, or maybe based on these variation quantum circuits to comprise such as large language models, to comprise classical neural network. So if we just do this unconventional hybrid quantum classical architecture, in such architecture, during training, we just use variation quantum circuits to do this training work. I use such a frequency to generate some older model parameters for the classical neural network. Maybe it's how to consider is a large language model. So it contains billions, 10 billions, it's a model parameters. So such a huge number of parameters can be generated by using a few few parameters contained in such a simple frequency. So use VQC to generate more than 10 billions is a model parameters for such as a large language model. So we can use VQC to control as a large language model. In other words, we do this model compression based on this quantum computing. And for this infra term, we just decouple this the link between the classical neural network and there's a quantum circuits. So if this test data come in, this only goes through this end-to-end classical pipeline without considering these any quantum components. But during the training, we just use such a quantum components, quantum circuits to generate these model parameters for this classical neural network. In doing this way, we just implement is a very primarily efficient. It's a large language models using this variational quantum circuits. So just call it unconventional hybrid quantum classical architecture and implement quantum enhanced machine learning. Okay, this is the brief introduction of our research about quantum enhanced machine learning based on how to use the quantum circuits to just enhance the machine learning performance in terms of model compression, or maybe use the quantum kernels to just implement some of the quantum features. But now today's our research focus about do the opposite thing. We have to consider this using the AI for quantum or using the machine learning to just scale up the quantum neural network. Our first work is about the architect this TTN VQC. We just combine this tensor train network in physics. We just call it a matrix product state combined with the VQC. So let's see this some challenge of this classical VQC. Classical VQC, well, it consists of 3 components. The first one we have to face about data encoding. Data encoding means that we have to convert some of this classical data into quantum states. And here is a challenge here that how to just implement this efficient data encoding, such as ongoing encoding. We also use by the lower dimensionality input. But normally, the input is of high dimensional. How to do this dimensionality reduction is one challenge. Another one side is I consider this parametric quantum circuit, even without considering this quantum noise. To optimizing such as the rotation gains is a non-convex optimization problem. It means that it's difficult to find a good global ponds or local optimal ponds using some SGD or gradient descent-like methods to just update such model parameters because it's a non-convex optimization problem. If you want to place such a quantum circuits on real ESQ devices, it's a problem become more challenging because you have to consider quantum noise effects. How to do this, that is the training process to be resilient to this noise effects. Maybe another new challenge. Okay, in our researchers work, we consider how to just do this combination between this tensor train network. Tensor train network is a one order, a very simple tensor network. Maybe this another name as MPS. So this tensor train network is just place it on top of the VQC. The VQC is here. User here is we just maintain the same architecture before as this like the same as this one, but we just use the tensor train network before such as this VQC architecture. The functionality of a tensor train network here is still this dimensionality. So this input is high dimensional. This input X is a very high contains a very high dimensionality. So we just use the tensor train network to do this dimensionality reduction. Also, we also do this here in between this tensor train network and the VQC. We just introduce some nonlinearity. So just in the feature space. So we know that frequency is a linear transformation from this input to output. But here in between this tensor tree network and this frequency, we just introduce some nonlinearity in the filter space. So we do this dimensionality reduction, and in between these two architectures, we just introduce the nonlinear activation functions to implement this nonlinear transformation. So just improve this expressivity because of introducing the nonlinear activation function. Also, we use the tensor tree network to just implement the dimensionality reduction from the this input high dimension to the lower dimension before going through such a VQC. So this is a basic idea of such architecture. Here we just do some mathematical analysis to show the upper bounds for each error component. So we just do this error performance analysis. This analysis is very common in classical machine learning theory. So let's see this whole picture. It's a whole family because it considers all functions. And this is a target function we want to approximate, and we do know beforehand. So we just select the operator from this frequency functional class. We want to find the optimal, the ideal the function, the frequency function from the smaller frequency functional class. But in practice, we just use some the training data to estimate such FD star. So we get it F star is the optimal operator using some of the machine learning training methods. But this considers optimization error between this actual optimizer and this ideal, the minimizer. So this can also consider is another optimization error. So how to this totally three error components: optimization error, is estimation error, and optimization error. If one just upper bound each error component and show that which factors determine such error component and how to just reduce such error component by controlling such factors. So let's consider the first one. The first one is we focus about approximation error. In such the combination architecture is a tensor tree combined with such as frequency architecture. We see that such architecture can be decomposed into a linear transformation based on the tensor tree network plus a nonlinear activation function that's placed in between such a TTN and the VQC. So there's a nonlinear activation function. And finally, that's the lower dimension narrative. This input goes through that VQC. So there's another linear activation function and the nonlinear transformation function based on such a VQC. So there's three function terms that can be combined together. So we can see that a linear transformation plus a nonlinear activation plus a linear transformation just identical to Sabanco and Barron's universal approximation theory. In such a theory, it's expressivity. But we see, in other words, you can say that function approximation upper bound is can be inversely to the root square of the cubic count. U means that here is the number of qubits. So we can just use the Sabanco and Barron's universal approximation theory to just upper bound, such as the combination, this architecture. Another thing is that here we consider using ongoing coding. So ongoing coding in nature just introduce another approximation error term. So just related to the depths of this the VQC architecture. Here we consider is M is the depths, is the layer of the depths of the such a VQC. So you also consider this ongoing coding to induce another error term. So just combine the two error terms, it just to compose the upper bound for such as approximation error. So this is the first error component by using some the balance Bango and balance universal possibility theory. Also considers ongoing encoding in nature, so that we can derive the upper bound for such a post-major error. Another thing is about estimation error. Estimation error is just n such as this the frequency functional class. So this the distance between this the training data minimizer and the ideal the target function in the ideal the frequency target function. So this estimation error. You want to just upper bound such as error term, it's just based on this upper bounding, this empirical randometric capacity. It's another terminology always used in the classical machine learning. So we can consider this composition of two functional class. One is the frequency, another thing is the TTN. TTN means the tensor tree network. Then we consider there is a common randometric capacity. It's upper bounded by each term with respect to is the TTN functional cost, and another thing is the frequency functional cost. Each term is we can just see that it's very related to the root square of the number of the training data. And here is the training data, and the PL and this lambda prime is associated with the model complexity of this the TTN function and the frequency function. So by increasing the amount of training data, we can give it a very lower upper bound for such as estimation error. So this the upper bound, and we derive for such a estimation error. So that's based on this randometric complexity. It just matters how well the function causes f can correlate with the random noise. So this we use such as the tool, the mathematical tool, to get this upper bound for this estimation error. Another thing is more challenging because consider this optimization error. Optimization error is just the measures the distance between this minimizer based on training data and the actual optimizer return this frequency the frequency operator. So there's a distance between this RS height and this the RS star, this optimization error. But we see this more challenge because we see that we have to face it's a terminology we call it barren plateau problem during this training on the frequency process. So ideally, there's one ideal path from the bottom of the mountain to come up to the top of the mountain. But in practice, we all stay on horizontal line. It means that it's difficult to find this ideal path or somehow to find this path to find the bottom mountain to come up to this top of mountain. So such a challenge we call this a barren plateau problem. But in such architecture, with such as a TTN frequency architecture, we want to just we can set it set up is the mu PL condition. It means that the first order of the norm function with respect to his parameters, we consider this R2 norm is greater than this mu this norm function value. If we can satisfy such a mu PL condition, we can just guarantee its exponential convergence rate. So it's just a convergence training rate can be guaranteed if this PL condition can be satisfied. So you just our experiment with us shows that here we just set a PL condition using such a TTN because in the TTN frequency architecture and combine with the classical frequency with using the PC to do this dimensionality reduction. Here we want to place in the environment in the for this regression task. Regression task, the input is current data, and output here also consider its output. Its output is a clean environment, so you can also consider it's a clean data. So we do this experiment to show is to measure this AE loss. You see that using such a TTN frequency, we can just achieve the exponential decrease of this AE loss values. But we consider this PC plus VQC is very difficult to get converged. So this in such as an experiment to demonstrate or corroborate our observation side is if we can set up the mu PL condition using the TTM VQC just tool, we can just exponentially increase its regression performance using such omnis data set. It's a more challenging environment. It's a more difficult environment. Is that we just input is a noisy data, so just correlate the input data with a Gaussian noise or using some Laplacian noise, and output is a clean one. The is using such as TTM VQC to do regression task. The input is a noisy input data, and noisy is a clean one. We do such a regression task. Here we show that is our this TTM VQC with A qubits. About 3 years ago, we just used this A qubits. You can see that also can maintain the performance, even though the input data is input data are corrupted by using some the Gaussian or Laplacian noise. So our experiment just to corroborate our theoretical contributions using the TTN to assist the development of VQC in terms of optimization, estimation, and this approximation performance. Okay, but here there's another unresolved problem is such as TTN VQC. The one is that we always set up PL condition beforehand, and it's difficult to set up it beforehand. It's no general case. In general, it's VQC cases, maybe it's done now. This satisfies such a PL condition in general. It's one unresolved problem. Another one is that for such a TTN VQC, it's not resilient to the quantum noise. So our this simulation that's placed in the clean environment is we do just simulate our results on CPUs and GPUs. We do without considering these the IBM quantum clouds using the on-queues quantum computers and not based on these actual quantum computers. So we don't consider the quantum noise. That is such architecture in nature is not resilient to the quantum noise. It's the second unresolved problem. So we have to consider is other new architecture and it's a new and the conventional architecture. Maybe how to use the tensor train network to just set up a new architecture to just better resolve such two problems. One is that we don't consider others. We don't use some assumption beforehand. We don't use a PL condition. We don't use other assumptions to guarantee the stability and the trainability. Another thing is that maybe it's a new architecture and this new architecture, and maybe it's resilient to the quantum noise in nature. So this year we have just put forward a new architecture. We call it a tensor hibernate VQC. So this tensor hibernate and this tensor hibernate VQC is also consists of two components. One is a tensor train network. Another is a variational quantum computing, variational quantum circuits. But previously, we just used a tensor train network for this dimensionality reduction, for this feature extraction. Here, this introduce a nonlinearity activation function in between this TTN and the VQC. But for such architecture, we do quite different. Here we can consider that the tensor train network, we just place it on CPUs or GPUs and just generate all the VQC's model parameters during the training process. So we can see that the log function is just a path only we can just link to this TTN. So the tensor train, these parameters contained this tensor train network can be trainable, can be updated during training process. But all the parameters contain such a VQN, maybe it's are generated from this TTN this model, from this architecture. But they are not participate in the training process during the training during the training process. All the model parameters is all the quantum gates that now this participate is update process. So all the parameters are generated from this tensor train network. And after training, we do the inference. We just decouple this link. When that all the data goes through this VQC, so we call it the quantum forward pass. It means that the VQC only do the inference and that's not get involved in the training process. And all their trainable data is all the parameters are just from this the generation of the TTN. So just in this way, it just overcome the difficulty of trainability inherent in such a VQC architecture. And we can use this the quantum advantage is in terms of speed to do some inference. For example, we can see that we use for this generative AI, we can use the quantum generative AI. So we use a VQC-based quantum generative AI to do the inference. But the difficulty is how to just get well-trained VQC. We can just use a tensor train network to help to assist the VQC to get us better trained is the parameters. So we can see that the parameter generation based on the classical tensor train network. Here, the VQC do not participate in the training process. And after training, we just decouple this link. We do consider the tensor train network. We just only consider the quantum forward pass and take advantage of the VQCs as a quantum power to implement is a quantum based the inference for these generative AI architectures. So this I have a new paper this year is based on such as architecture. That's the tensor meta. Okay, just use another name. It's this we use a tensor harbor as a VQC. Here just a tensor train guided is a meta parameterization framework for variational quantum computing. I'll give here just I will show this the most important theoretical result is such architecture. We just give us a generative upper bound, so this the upper bound for expressivity. But I think it's the most important one. You can just demonstrate such architecture is the noise resilient. So we just consider this the noise can be induced during the training process. So we do this gradient descent how to consider this all kinds of data, this noisy kinds. Maybe this the mu here, maybe it's IID, it's not IID, it's sub-Gaussian with some but here we just can assume that it's a zero mean. If this this another mean, we also can just it's more difficult. But here we just consume is a zero mean, and the mu here. Sorry, this is tau here. Tau here is can be ID Gaussian, ID sub Gaussian. Maybe it's this non ID is a quantum noise. Can be introduced here. Can be it's a sum to this ideal gradients. So this consider this because we just decouple the training and inference. So this W is the VQC's parameter, and this the G here is the model parameters contained in such a tensor train network. So this we do this partial derivative. So the gradients can be take partial derivative and consider this the R here is a null function. So the first derivative is with respect to is a VQC's parameter. And the second one is the model parameters of VQC. It depends on this model parameter contained in such a tensor train network. So there's another partial derivative. So we have to multiply such a two partial derivative together to compute this the gradient descent. But for the first partial derivative, there's a quantum noise get involved. And such a quantum noise can be ID or non-ID or other kinds of quantum noise. Our theoretical result shows that we take the variance, but here we just consider is the mean zero, so we just take variance. Take variance. It does show that our final this theoretical result for this variance for this for gradient term inside is can the It's a noise effects can be diminished to zero if we can just increase the number of qubits, or maybe it's a set up more layers. It means that the quantum effects can be diminishing using such as this unconventional architecture. Even though it is we just consider the quantum noise on actual quantum computers, but in such architecture, our result that this architecture is quite noise resilient. So this show why such architectures can be very, very practical on real quantum computers, because we just train our models on the classical computers, but do this inference in the real quantum computers. And then such a real quantum computers parameters are just based on the generation from this tensor train network. It's a classical, it's a network. So this unconventional architecture. Okay, as such a conventional architecture is the noise resilient against such a quantum noise. Okay, we can just give you two examples. I will show many, many examples in our paper. Here, one example is a quantum machine learning based on the quantum dot classification. We do the binary classification and uses quantum dots. So this using quantum data to show that our the methods or advantage. Here we can see that it's a full picture. The first picture we see that our using some with tensor meta we could see is our neural architecture, and compare with we could see and the TTM we could see. TTM we could see our previously proposed architecture. We show this the accuracy based on our new architecture can outperform is the TTM we could see, and significantly outperform the classical we could see without any TTM's assistance. And also compare with the classical one. Classical one based on some pre-trained classical neural network, the ResNet 50 plus the low-rank adaptation method. It's nowadays a state-of-the-art this machine learning method using the large language model. Also can see that our just proposed method shows an advantage over the classical ones. And more important thing is that we just as Poisy on real quantum computers. Here just do a simulation that we just introduce the quantum areas to each quantum gate. And we see that it can see this the performance can be stable, even though there's the corruption of the quantum noise. And on the paper also shows some more experiments about that place our this method on real quantum computers. Can be seen as more even the real quantum noise come in is such a method can be also very noise resilient. Here we use 20 physical qubits. Another thing is that we do this quantum optimization. Here we consider the method of the problem. So here's a classical QAOA is also based on variational quantum circuit. Compare with our proposed one, our this new architecture, we see that even if we use our new proposed architecture, the improvement is average above is 16.34% increase, the relative increase. So this we see is a significant improvement based on the new we could see architecture. Another thing is that we just place it in some the quantum error environment. We can also see that improvement is of more than 15% improvement. So we just using such as quantum optimization for this maximum cut is a problem and show his quantum advantage using such our tensor hyper we could see architecture advantage in dealing with some the quantum optimization problems. Okay, so let's give it a final conclusion. My research about is quantum machine learning. It can be divided in two parts. One part is quantum enhanced machine learning. So we just propose some quantum reinforcement learning algorithm and then propose some quantum CN architectures. And we just set up this unconventional quantum classical hybrid architecture using the quantum to just to do some model compression to this large language model. So we just implement parameter efficient large language models based on the quantum circuits. But more interesting is about is using AI theory for quantum. So we just using the tensor train network to assist the development of the frequency. Also can just use set up unconventional tensor train combined with the frequency architecture, just decouple the training and inference to implement such as a very energy resilient architecture to dealing with and resolve problems in trainability, in expressivity, and you also can improve his generalization capability of the VQC architecture. Okay, this is my recent work. Thank you for your attention. Please let me know if you have any questions.
Thank you. Is there any question? Can I ask one question?
I have
Okay,
one
please.
question.
Oh, sorry. Yeah.
Can I ask you? So, in the beginning, you showed some slide about the several methods has a quantum speed up. For example, quantum Boltzmann machine has square root n speed up. So, which reference explain this one?
Okay. Just a copy just from this Nature paper. That is in this paper, it shows that we have a very for total quantum computers. We just realize is at least quadratic speed up, but such an algorithm. Here is a quantum SVM, quantum PCA, and quantum reinforcement learning, and for that neural network, is if the preset algorithm of for total quantum computers, perfect quantum computers, is the speed. We can just using the speed is a training process more than quadratic. We can just implement quadratic speed up. So we use a fewer time with a later time just to finish the whole this training.
Which reference show this one? Which reference? Nature? Which Nature paper?
It's a Nature paper. I'll send you this paper name. This maybe it's
Okay.
quantum machine learning Nature. You can just check as quantum machine learning Nature. You can just find this. I'm sorry, I just don't give you the reference. Here, just the table. There's a table. There's from this from Nature paper about 2017.
Anyway, so I need the reference. So because I'm quite confused. So and also there are several problems. So you slightly mentioned that the relation with Plato, but I could not find because quantum variational circuit. This one has some serious problem about the Plato problem. But you mentioned that you VQC does not have a Plato problem. I'm very confused. Maybe you
Okay.
mentioned this method has a problem about Plato. So, but you mentioned that you mentioned that this one is not so serious.
Okay, just understand. So, I just want to do this compare this the basic performance directly using the pure quantum computers. To use the quantum these architectures, we just use the classical to assist the development of the quantum circuits. So so our method is based on the hybrid model. Hybrid model is based on some parts from the classical component, some parts from the quantum components. So we can achieve some of the quantum advantage by using the hybrid quantum classical architecture instead of this the end-to-end quantum architecture. If we use the pure quantum machine learning, maybe the current performance is quite poor. But that's why I have to just transfer some knowledge from the classical architecture, a classical machine learning theory, to assist the development of the quantum pipeline. So that's why you will see that we just find some quantum advantage on some tasks of machine learning or some tasks of the optimization. So that's my research is that to just set up this unconventional architecture.
I'm slightly confused. You used simply a gradient method, but I think gradient method has problem for Plato.
Yes,
So
this
first idea. So and also your method is quite common. So many people using the similar method.
similar method. I think it's I propose I propose unconventional method. And conventional method means I'm just using this not quite different from the other people's method. For example, in this one, this is my unique method.
Which part is different from the conventional VQT method? Which part is different?
A conventional method maybe also is this one maybe can be seen as a conventional one. Conventional one is this maybe use this classical one, a classical neural network, classical component before this we could see. You know, it's a hybrid quantum classical architecture can be seen the classical one. Maybe it's many years ago, it's just 3 or 4 years ago, it's just so many people propose that architecture. But nowadays we see that this architecture face many problems. That's why I say that we have to see unresolved problems. So, but for such architecture, if they can satisfy such a PR condition, I mean, we can just perform well on some task. But it's difficult to set up such PR condition. So there's need some assumption to guarantee such as a classical method. For such a method can work well on some this machine learning task. So that's why I'll give you the new it's a general architecture. So also can combine this the classical component with this the quantum component. We just devise some this unusual, this unconventional architecture, so it becomes more general to this machine learning task. So this don't need to just satisfy some pre assumptions. Okay, thank you for your question. And other comments or suggestions? Okay.
Okay.
Can I ask a question?
Oh yeah, no problem.
How do you specify the map from TTN to BQC here? So I think there are various
Okay.
ways to map
Okay.
the parameters obtained in TTN to, parameters
Okay.
in BQC. Is there any guiding principle or, just empirically testing the other ways?
Okay. This a TTN is a place before the VQC. So just here. Just to give you clarify something. It's the input is the D dimensional and the D dimension. So the D is much greater than the U. U maybe considered is a qubits. So the TTL here, the functionality of the TTL here is due to this dimensionality reduction from very high dimensional to the lower dimension. So this we do such as dimensionality reduction. But here we just after this dimensionality reduction, we just let this the feature do some nonlinear activation function. So because of such a nonlinear activation function, we consider this a nonlinear. We just introduce some nonlinearity in the feature space. So this the main functionality for such as TTN component before this VQC. We saw such a TTN. You can see the performance quite poor. But we combine such a TTN. You can see that we can somehow an exponential convergence rate during training. So this the advantage. We see this advantage of using such a TTN to assist the development of the VQC. So this about 3 years ago, that found that using such a TTN can greatly improve this VQC's performance.
Okay, but what about the meta TTN part?
Okay, the method. Sorry, meta.
Yeah.
Okay, you say the decimal. You
Yeah, that's
just
fine.
mentioned this one?
Yeah.
Yeah.
How
Okay,
do you
okay.
generate VQC's parameter? Is it just not just dimension reduction, but you also need some
Oh,
filter?
okay. Okay, for such a TTN, we just using such a TTN to generate the model parameters. Here, okay, but here for such as for such a the input, for such just using this amplitude encoding. In now previously we just consider ongoing coding, but for such architecture, we just consider such quantity states are given beforehand. So we can using also combine with another as our previous TTM we could see you consider this the ongoing coding. So but here this the functionality for such a tensor train network is to generate the frequency parameters. So there's two paths. The first path is a parameter generation during training. Another path is a quantum forward path. So after training, we do consider it's a tensor train network. Only that the quantum code features goes through the frequency. So we just call it a quantum forward path. So decouple the training and the inference. That is the frequency to just participate only the inference power size and let this tensor train network combined with the frequency to get involved in training, but we can only consider the tensor network's parameters. We only update the TTN's parameters. But here is the frequency parameters can be not fixed. It's generated from this TTN.
Okay, so
So this
somehow that part is pushed to the optimizing tensor network part.
yes, only optimizing such a tensor train network. We
Okay.
don't directly optimizing such a frequency parameters. So running in such a way, so we just overcome some the noise effects because the noise effects varies with series in the frequency training. So how to just improve his trainability? It just using the CAS one, the CAS architecture to generate the Cs to generate such as frequency parameters. So CPU and GPU, we can just avoid the quantum noise effects.
Okay, thank you. So the time has come, so let's thank the speaker again.
Okay. Thank you so much.
Thank you. So we will start next talk when the speaker is ready. Okay, we can see the slides.
Okay.
Can we start now?
Sure. Hello, everyone. It's a great pleasure for me to be here and to have the opportunity to introduce one of our recent work in quantum metrology. And it is actually collaborated with Haidong from CUHK and Yu from Tencent. And the title of the talk is Quantum Metrology Enhanced by Leveraging Informative Noise with Error Correction. So it is the intersection of quantum metrology and quantum error correction. So the talk is going to be divided into 4 parts. First, a brief introduction on quantum parameter estimation. And the second part is some brief review for the precision limit for Hamiltonian estimation. And then comes our main result of the ultimate precision beyond Hamiltonian estimation with the assistance from quantum error correction. So first, let me brief introduce the scheme for quantum parameter estimation. Traditionally, if we have some parameter which may related to some physical quantities, such as the phase or the magnetic field, it is usually related to some dynamical process, maybe unitary or maybe some more general dynamics. And to estimate this parameter theta, we need to first prepare some quantum state, which is also called the initial state. Then we let this initial state evolve under this theta-dependent dynamics. And then we obtain the final state, which is dependent on this theta. And then we can choose arbitrary quantum measurement, and then obtain some classical data. And actually, this classical data will dependent on the parameter of interest. To estimate this theta, we need to first make some assumptions. First, we require the dynamical process, this E theta, should be given and fixed. We should have some prior information about the dynamical process, which is also natural for an explicit experiment. And the second assumption is that we require that all quantum operations should be accessible and perfect, including arbitrary quantum measurement and quantum control. Under these basic assumptions, a natural question is that what is the highest precision of estimating this theta given a fixed dynamics E theta? To solve this problem, the direction is actually backward from the optimization of the estimator for classical data. Actually, this has been solved classically many years ago. The optimal estimator is usually the maximum likelihood estimator given any classical data. So using this optimal estimator, we can achieve the classical parameter bound, which is given by the inverse of the classical feature information, short for the CFI. And to achieve this CFI, the optimal measurement we have to do should be optimal. And one such optimal measurement is given by the spectral decomposition of the SLD operators of the final state, that's denoted as L theta. And given the fact that we are using the optimal measurement, the precision is further determined by the quantum feature information. We write it as the QFI. So the optimization in quantum parameter estimation then becomes the optimization of the quantum feature information of the final state. And it includes three parts. First, the strategy, how to perform the experiment. Second, the quantum control. We can use the control to alter the dynamical process to make it more efficient. And finally, we can also do optimization over the initial states. So next, we will going to show the optimization of these steps by focusing on the quantum feature information of the final state. And actually, there already exist many systematic studies on this topic, which generally focus on the estimation of some parameter in a Hamiltonian. Let's call it Hamiltonian estimation. Actually, the simplest case is that the dynamical process and the proof states are both fixed. In this case, the final state is also fixed. So we can directly calculate the quantum feature information. In the noiseless case, which is the simplest, the dynamics is given by the unitary operators related to the parameter x, which is we want to estimate. And substitute this final state into the formula of quantum feature information, we can easily verify that it equals to 4 times the variance of the generator of parameter x. And here, this is the definition of the generator. And also a further calculation will give us the optimal states that maximize this variance Actually, it is the superposition of the eigenstates corresponds to the maximal eigenvalue of the generator and the minimal eigenvalue of the generator. With this optimal state, the maximal QFI equals to the maximal eigenstate minus the minimal eigenvalue, and then take the square. This is for the noiseless case, but in general, quantum systems should be usually open, and the dynamics uh, is noisy. And even for the Markovian case, the calculation will be much more complicated. And for the noisy case, the dynamical process can be written in the cross representation with this KLX being the cross operators. So given these cross operators, uh, we first know that we can first calculate an upper bound of the quantum Fisher information, which equals to 4 times the mean of H1 operator minus the mean square of H2 operators. This is a result given by the previous paper. So this is just an upper bound. And actually, we also know that the cross representation should not be unique. There should be unitary degrees of freedom. So by optimizing over all the representations of the cross operators, we can get the tightest upper bound of the quantum Fisher information. And in this paper, it has been proved that the tightest bound, which corresponds to the minimize of this value, exactly equals to the quantum Fisher information. And based on this result, we can, by doing further optimization over the initial states, we can even calculate the maximal quantum Fisher information for all initial states, which is upper bounded by this formula, which includes some optimization over the representations of cross operators. So this is the ultimate precision without quantum control. And these two formula, we can also call them the channel QFI because we already optimized over all the initial states. And actually, we have additional degrees of freedom in the dynamical process by arranging the multiple quantum channels in parallel or in sequential. And most importantly, for the sequential scheme, we can even add additional controls in between the two quantum channels. And actually, sequential scheme has a strict hierarchy over parallel scheme because by choosing the controls O1 to ON to be the swap gates, we can simulate the parallel scheme. And furthermore, we can even adaptively alter the controls O1 to ON which is also called the adaptive controlled scheme. And in the general sequential control scheme, the dynamics is given also sequentially with cross operators defined also in a sequence. So this is the control enhanced quantum parameters estimation, and we are certainly curious about the optimal precision in this control enhanced scheme. So let's proceed. And for the general Markovian dynamical process, we actually have two different ways to describe the dynamics. One is the cross operators, and the other is the Lindblad master equations. And they are actually equivalent up to small time expansion. So for the general Markovian case described by this master equation, by dividing the time into many small time intervals, for each small time intervals, the dynamics can actually expand it into the cross operators in this form. And by substituting the expansion to cross operators into the channel QFI, just as before, we can also get an upper bound for the quantum feature information given in this block. And we can see that it is possible to achieve a t-square scaling of QFI, which is good for quantum metrology, because that means if we take the time longer, then we can get a quadratic improvement for the precision quantified by the quantum feature information. And obviously, to achieve this t-square scaling, we have to require the norm of this beta dt operator to be non-zero. And it indicates if we calculate this beta dt, we can obtain that it is equivalent to a condition that the generator G should not be in the span of the Lindblad operators. And two research groups almost simultaneously find this condition. And this condition just give a criteria whether we can achieve the t-square scaling, but it we have not shown how to achieve this t-square scaling. And the key is to effectively eliminate the quantum noise, because if we have the quantum noise, then we will always achieve the standard quantum limit given by linear t, not the t-square. So how to eliminate the quantum noise? Actually, quantum error correction is one of the universal methods to correct the quantum noises. And this figure shows a simple round of quantum error correction. Given a quantum state psi with the assistance of additional qubits, we can encode the information into a larger Hilbert space and let it evolve under the quantum noise on the original system, and then doing some syndrome measurement to detect whether some error happens, then perform a recovery operation when some error actually happens. So after the quantum error correction, we should perfectly recover the initial quantum state, rho C. And here this E describes the noise and R describes the recovery operations we actually perform. And to perform the quantum error correction, the assumption is also basic. We can characterize the quantum noise in such as the cross representation. So the task in quantum error correction is to construct the QEC code and also the recovery operation for a given noise. And there is also criteria for the quantum errors to be correctable, which is basically first it should be detectable, and second the errors should be distinguishable. And in a formula, it is given by the KL conditions, which corresponds to this formula. And such KL conditions can actually be transformed to quantum metrology under the Lindblad under the Markovian noise. So we already decompose the Markovian evolution into small time sequence with cross operators already known. And we also have this theorem. So the next step is to construct the QEC code. And actually the QEC code is given by the orthogonal complement of the generator to the Lindblad span. And the KL conditions in quantum metrology actually can be translated into these three conditions. And for the last one, it is unique for quantum metrology. And it means that on the code space, the encoding of the parameter should be non-trivial. And with quantum error correction, with the recovery operations, the dynamics will be perfectly unitary, and Heisenberg scaling can be achieved, which is with effective generators given by the projection of the original one into the code space. So this is the previous result. Let's call it the ultimate precision for parameter estimation in Hamiltonians. So next, we can go further and consider the ultimate precision beyond Hamiltonian estimation. So previously for Hamiltonian estimation, the parameters are encoded in the Hamiltonian H. And we also have the noise spectroscopy, which corresponds to the parameters inside the quantum noise. In master equation, it's just encoded into the Lindblad terms. And actually, the most general case is for the so-called correlated parameterization with parameters encoded in both the Hamiltonians and the Lindblad operators. For correlated parameterization, we also say that the noise is informative because the Lindblad terms is also dependent on the parameters of interest. And we can illustrate the idea with quantum hypothesis testing because they are actually the same thing with quantum parameter estimation, both characterized by some statistical distance of two quantum states. So for the quantum hypothesis testing with correlated Hamiltonian and noise, we are using some quantum states and let it evolve under different Hamiltonians and obtain different quantum states. By doing measurement on these two quantum states, we are required to make a guess on which edge we are given. So in the case that the noise is not correlated with Hamiltonian, we can the statistical distance of the final state should be reduced, and with the successful probability is also reduced. But for the case that the Hamiltonian and noise are correlated, then the shape of the noise are potentially dependent on the Hamiltonians. And in this case, the statistical distance of the final state is possible to be enlarged, which may help us to do the quantum hypothesis testing. And some experiment has been done to verify this theoretical result. And this is for quantum hypothesis testing. And what is the case for quantum parameter estimation? So in quantum metrology, how to utilize such correlation in Hamiltonian and the noise, and also what is the full potential of informative noise. By combining these two questions, we further ask what is the ultimate precision for correlated parameterization. So this is a this is a key question in this talk. We can start from a toy model. Let's consider the estimation of a fluctuating magnetic field, which for which the dynamics is given by this Hamiltonian equation. And here we consider the estimation of the direction of the magnetic field, which corresponds to this theta. And this is actually the 2D magnetic field with direction characterized by this sigma n. And the spatial thing is that we have the white noise along exactly the same direction of the magnetic field. And this noise is assumed to be Markovian with a white spectrum. And this dynamics can be equivalently described by the effective master equation with Hamiltonian given by B sigma n and Lindblad operators given by sigma n. This is actually describes the dephasing noise along the magnetic field. So next we consider the ultimate precision under the sequential scheme with additional quantum controls. Our first observation is that for the estimation of theta, the noise term, which equals to Ct times sigma n, is informative because this term is dependent on the parameter theta. Yes, and actually for each trajectory of the quantum noise described by Ct, the generator of theta can be calculated with the original formula. And we also observed that the control strategy for Hamiltonian estimation, the optimal one is to make seems to make this U tau equals to identity. And if we can make this U tau equals to identity, we can directly calculate the quantum Fisher information, which equals to 4 times the variance of the generator h theta, which further equals to 4 times b squared t squared plus 4 times gamma t. And here we note that this 4 times gamma t is benefit from the noise term because it is linearly growth with the strength gamma. Yes. But the question remain unanswered is that how to design controls such that this U tau, the effective dynamics, equals to identity for each trajectory. And second, is this improvement already maximal? Can we further improve this quantum Fisher information? And at last, how to identify the ultimate precision and further achieve it? And we will answer these 3 questions in the next slides with under even general Markovian dynamics. So we think the toy model is too simple. We just start from the general Markovian dynamics with Hamiltonian dependent on x and also the Lindblad terms dependent on x. For the general Markovian dynamics, we can similarly divide the time interval t into many small intervals with length dt, and substitute the cross operators into the upper bound of the QFI for the sequential scheme, and we obtain a formula that looks similar to the previous result, also with t-square scaling, which can be achieved if and only if the norm of this beta dt does not equal to 0. So substitute the cross operators into this beta dt. Here comes our main theorem that the Heisenberg scaling can be achieved if and only if this h hat does not belong to the span of the Lindblad operators. And here we call Heisenberg scaling because we achieve the t square here. So it is with respect to the time, which is also a result in quantum systems. And our theorem looks similar to the previous one, but there are many differences. First, our result is not limited to linear Hamiltonian because here we take the dot of Hamiltonian, not the generator. And also here the generator of x is noise. The effective generator of x is noise dependent because we have additional term that is related to the Lindblad terms. And last, the Heisenberg scaling may be achieved even when the Hamiltonian is independent of x, which means that for noise spectroscopy, with if we can realize the control, we can also achieve the Heisenberg scaling characterized by t squared. So the most important question is how to achieve the Heisenberg scaling. Yes, our answer is that, and if the condition is satisfied, an explicit adaptive QEC strategy can be constructed to achieve the QFI scaled with t squared, with additional non-negative term scaled with t. Yes. And actually, the QEC strategy looks similar as before. We just do the projection of the effective generators into the Lindblad span and take the orthogonal complement and use this orthogonal complement to design a two-dimensional QEC code. And we also know that this two-dimensional QEC code, the code space, will be dependent on the parameter x because the generator is dependent on x. So our QEC strategy should be designed adaptively. And by adaptively updating the estimation of x, the QEC conditions should be asymptotically satisfied, which is characterized by these two formulae. Later, we will provide numerical significance that the adaptive precision can actually work. And with the QEC code successfully designed, the prop state can also be chosen as the projection onto the code space. And our next step is to analyze the effective dynamics under the quantum error correction operations. So originally we have the state evolve with quantum noise, and then our syndrome measurement is the projection onto the code space and outside the code space. And then the rho m is the post measurement state and can be written as this formula. And these two terms are actually equivalent but with different physical meanings. For this mk, it says that the noise ek will drive the state out of the code space, characterized by the I minus pi c. And for this second form, it is actually calculated by polar decomposition. It shows that the error ek effectively are rotations on the code space, and luckily these rotations are orthogonal given the QEC conditions. So combining these two facts, we know that the errors are first detectable and also distinguishable. With these two facts, we come to the conclusion that the noise is correctable with the QEC code. And the recovery operation is actually rotate the states back to the code space. So if UK error happens, then we apply UK dagger. If UM error happens, then we just use UM dagger to rotate it back to the code space. And yes, after the rotation, the aggro corrected dynamics should be complicated and cannot be analytically solved. But luckily, for the effective dynamics around the true value, x equals to x hat, we can expand the dynamics on the right-hand side of the master equations into this form. And with the expansion up to the second order of dx, the QFI can be successfully calculated analytically using the Buris distance, actually equals to a quarter of quantum Fisher information. And finally, we can obtain the QFI with a given initial state per psi, and it is equals to the equals to two terms. And the first term is the variance of the effective generators related to the noise, and the second term is a non-negative linear benefit from noise operators. So this is a general result for arbitrary Markovian dynamics. And also let me summarize our adaptive QEC protocol to achieve the precision in the last slide. So first, we need to prepare the initial state as a pure state in the code space, and the optimal one should be the superposition corresponds to the minimal and maximal eigenvalues of the effective generators. And the second step is to repetitively apply the recovery operation with cross operators consisting of the different rotations corresponds to different errors. And the third, perform projected measurement on the eigenvectors of the SLD operator of the final state, which should also be in the code space. And at last, we repeat x hat. We update the estimation of x hat, and this is just a single run. To adaptively update the parameter, we have to substitute this estimation x hat back to the first step and again design the second initial state and then repeat these steps. So we can also provide a geometric interpretation that how our noise enhancement work. So we let this black line to describe the original unitary evolution, and when there is no noise, then the quantum Fisher information is described by the distance of these two unitary evolutions. But for the correlated parameterization, the neighboring dynamics still contains the noise because it cannot be perfectly corrected by the quantum error correction. So the noise makes the neighboring dynamics more different from the unitary case, and this makes the additional enhancement happens for the informative noise. So this is a theory for general dynamics, and our last step is to revisit our toy model and see how it works. So for the dynamics described by this master equation, we know the Hamiltonian. We also know the noise operators. Then let's substitute these two operators into our main theorem, and it can be verified that the Heisenberg scaling can actually be achieved. And the code space can be systematically designed, denoted as C0 and C1, with complement C2 and C3. These four bases can constitute the whole space. Applying the recovery operations and performing the optimal measurements, we can obtain the final QFI, which scales quadratically with t squared, with even additional improvements characterized by gamma squared t squared. So this figure shows the robustness of the errors dt for the estimation. And we also do the numerical simulation of the adaptive QEC protocol. And here these two figures shows the simulation for the estimation of theta and the mean square errors over 10 adaptive steps. And this figure on the left and on the right, the difference is just the initial guess. One is half of pi and one is pi over 4. So let's just look at the left figure, and we can see that this theta hat converges quickly to the true value within several steps, and also the precision of our protocol given by these circle ones surpass the precision of unitary parameterization given by this blue line. And also, it can be seen that as the estimator of our protocol converges faster compared to the unitary dynamics, because for the red symbols, it approaches the true value more faster than the blue symbols. So this is the numerical simulation. And our theory can even be extended to time-dependent master equations. So for the estimating the rotating frequency of a fluctuating field with additional time dependence of the magnetic field, by applying our results, we can see that the final QFI is with t to the power of 4 scaling with additional improvements gamma square. Someone also call it the super Heisenberg scaling, but this is actually the same as the Heisenberg scaling in principle. So actually, for the time-dependent Hamiltonian, our result still works, and the numerical simulation also shows that our protocol will make the estimator approach to its true value more faster and also with smaller mean squared errors shown in this figure. Yes, this is actually our main results, and let me do a summary. Our study generalized traditional schemes where only Hamiltonian is informative. We consider that the noise may also contain information on the parameter of interest. And based on this, we provide necessary and sufficient conditions under which the precision achievable in the presence of informative noise can reach the Heisenberg scaling given by this formula. And further, we construct an explicit adaptive QEC strategy to achieve the Heisenberg scaling given by this JQ. So based on this fact, we successfully show that informative noises can actually be exploited to improve the precision limit characterized by the quantum Fisher information. So that's the end of my talk. Thanks for attention, and any questions are welcome.
Thank you. Any question?
Okay, I have one question. So why you choose the Heisenberg scale? No, why use the Fisher information as a figure of merit for the Heisenberg scaling?
You mean why use the quantum Fisher information to
Why?
Because here in the sequence, we want to consider the problem that the system continuously evolved, and by doing error correction, we keep the coherence, and with time growing, we want to make the precision also improve. So here we use T as the results instead of the particle numbers n. So this is we think it is.
Why you focus on the Fisher information? Is there any proof to explain that Fisher information describe the precision of the estimation?
Yes.
You are considering the estimation error, not Fisher information. Fisher
Yes.
information is only the some quantity, not the estimation error.
Yes. Actually, in classical parameter estimation, the precision is
Now
characterized
you are
by the
considering quantum.
uh-huh.
Quantum, okay. Classical case, you are continuing the same distribution, IID condition, okay? In the classical case, you are considering the independent and identically distributed condition. Under that condition, Fisher information works well for estimation. This is assumption. But now you are considering quantum case, and there is no IID assumption.
Yes, we actually in the quantum case, we also need the IID condition.
No, where is no distribution? No distribution. You didn't consider distribution, only you considering the application of the same channel. This is not a distribution. We have some result only with distribution, no quantum channel.
Okay. So actually, we choose to use the quantum feature information because we suppose that the measurement and the estimation is already optimized, so that the quantum feature information will give the optimal precision.
No, there is no proper proof. You need to, in order to claim this, you need to assume so many assumptions.
Yes.
That kind of feature information does not work on the single copy case. You only consider single copy case.
Oh, we consider the repetitive measurement. We have to perform quantum measurement for many, many times to achieve to obtain many classical data, and then we perform the estimation.
In that case, this is very strange. For example, you need to consider n batch, for example, you consider m copy, m collection of the some optimization of the feature information. So, and you repeat m times. So, and then in that case, you increase the order n square and times m. So, for example, in that case, you need to consider n square times m square. But in that case, m is the repetition of the same measurement, the same experiment. So only you consider n copy of the single system. So in that case, you can achieve the order n square times m. But in the total use of the channel is n times m, and it's square. You need to consider that order for the Heisenberg scaling. That kind of
Okay.
calculation is totally incorrect.
Okay, I know. I got what you mean. For by repeating the measurement, for example, m times, then the quantum information should be multiplied by m.
Yes.
Yes.
So in
And
that
here,
case, the Heisenberg scaling should be defined based on m times m.
yes, that is actually the traditional definition of Heisenberg scaling. So here we may the here we call t square as the Heisenberg scaling, maybe some maybe misleading because it
Of
is
course,
not
quantum
the
computing.
traditional
So very
one.
confusing. So you need to consider total use of channel, and you need to exactly evaluate something like error, behavior of error. But there is no
Yes.
discussion about error. You only discuss feature information.
Yes.
But essentially, this kind of problem already solved by using the group covariant theory. Already exist. And in that case, the Fisher information coefficient, optimal Fisher information coefficient is not achievable. Already
Mhm.
exists that kind of theory. And also, I already recently shown that that kind of the super Heisenberg scaling, that is impossible, even with the error correcting code. This is
Yes.
impossible.
Yes. For that term, I think
Claim that they mentioned that that kind of hyper Heisenberg scaling is possible. But that person previously already shown that this is impossible. So his paper is somehow like the contradictive. So this is Julia's result. Julia's paper is quite confusing. Previously, he showed that super Heisenberg scaling is essentially impossible. Many years ago, he already shown that, but he forgot. Then recently, he showed that super Heisenberg scaling possible.
yeah.
Quite strange.
Yeah, actually, this term is also some there exists some misleading things.
Hmm?
Mhm.
But Julius group, he proved that the super Heisenberg scaling is the sense of the Fisher information. You repeat
Yes.
the similar result.
Uh, uh, I think we do not use similar. Uh,
the time is limited, so please discuss more details after that. So if there's no any further question, let's speak again. Is there any closing remark? If not, we will start tomorrow's session at the same starting time as today.
Sorry, so I forget one important thing. So today in Shenzhen side, unfortunately, typhoid attacked to us, so we cannot organize Shenzhen venue. So we have to switch this one to the online style. So this is quite unfortunate. So tomorrow, I believe that typhoon already gone. So maybe we will organize Shenzhen venue. So we will open that conference venue inside the Chinese University of Hong Kong, Shenzhen. So please come to Shenzhen campus. So even though you already finished your talk, you are very welcome. So please come to our campus. So thank you very much.
Thank you. So that's all for today. Thank you very much.